In this video, I introduce weight, mean, and variance communication for neural network training. Gaussian functions are central for many machine learning models because they form the basis for probability distributions. Since the sum of a large number of independent random variables will tend towards a Gaussian distribution, regardless of the original distributions. A key property of Gaussian functions is that the sum, product, and combination of Gaussian distributions is also Gaussian distribution. A standard way of limiting the amount of information in a number is to add zero mean Gaussian noise, which means that a noisy weight has even more expensive to communicate than a precise one, since it appears that we need to send a variance and a mean of a Gaussian distribution. Minimum description length framework makes very noisy weights to be communicated very cheaply. As shown here, this neural network, this input, this output. We have the weight distribution between each layer. In the traditional neural network training, we use a gradient descent to search the optimal model parameters. However, right now we use this zero Gaussian as a carrier wave. Its mean and variance is used to optimize the cost function. The goal is to minimize the cost function of neural networks, namely expected description length of model weights and data misfits, by optimizing mean and variance of Gaussian distribution at each independent weight, namely minimizing description length of a neural network. Assuming the prior distribution P of both sender and receiver is Gaussian distributed for a given weight. After learning, the sender has a Gaussian posterior distribution Q for the weight. The number of bits is required to communicate the posterior distribution of a weight is equal to the KL divergence from P to Q, as shown here and in this figure. Having sent the precise weights, the sender then communicates the data misfits achieved using these weights. The receiver receives the weights and misfits and then produces the correct outputs. For Gaussian with different means and variance, the KL divergence becomes this formulation. Next, we compute the data misfit cost, namely the expected value of this formulation, which is caused partially by the semantic errors of a network and partially by the noise in the weights. For a feed-forward neural network with one hidden layer and one linear output layer, as shown here, the expected square error can be calculated exactly. Assuming the weights have independent Gaussian noise for any input vector, the mean mu x h and the variance v x h of the Gaussian distributed total input xh are computed and received by the hidden unit h as shown here. Similarly, the mean mu yh and the variance vyh of the output of a hidden unit are computed even though the output is not Gaussian distributed, as shown here. Since the noise in the outputs of the hidden units is independent, they independently contribute each linear output unit. The noise weights WHG also contribute variance to the output units. Since the output units are linear, their outputs yj are equal to the total input they receive, xj. On a particular training case, the output yj of output unit j is the random variable with the following mean and variance as shown here. This mean and this variance. The mean and variance of the activity of output unit j make independent contribution to the expected square error EJ. If the ground truth of output J on a particular training case is dj, so the EJ is given by this equation. For each input vector, the value of EJ is used to compute backpropagation of the exact derivatives of E through the hidden units. The gradients of expected square error with mean and variance of input units are given by these two equations. For more details, please check with these references. Thank you. Bye.